Hello, everyone. My name is Mohammed. Today we'll be talking about building systems to monitor model health in production system. It's a mouthful, so bear with me today. So hello, Data Council. I'm fairly new to the community, so thank you so much for having me today. And hello to everyone else who's new to the community as well. A little bit about what I do. I'm a software engineer by background, but mostly focus on building tools, SDKs, and platforms for engineers and data scientists. I spend a lot of time thinking about design patterns for technical platforms built for engineers, data scientists, and more. Previously, I spent a few years working as a data platform engineering team at Shopify, where I focused on building analytics libraries, specifically leveraging streaming technologies like Apache Kafka. Right? A little bit background about Dessa before I get started. We build tools to help machine learning engineers in various enterprises scale up their machine learning workflows. Specifically, we are aiming to build the same kind of continuous delivery mechanisms as regular software engineering, but specifically focused towards machine learning. Our products include things like Python SDKs, schedulers, and more. Currently, I work on our suite, which is called Foundations. And Foundations is really our suite for continuous delivery. It's broken down into two products, which is Atlas, which is available to download for free, actually. And it's a machine learning development tool that converts your infrastructure into a platform as a service that your data scientists can collaborate on. The second tool, which is going to be the focus of my talk today, is Foundations Orbit. Which is really our tool for post-production model monitoring and maintenance. So I'm going to be talking about kind of the design principles that we use there, the implementation details, and what the architecture looks like. So you can actually go in and either build a tool similar to what we have in your own company, or explore this further, right? Okay. Outside of machine learning, you may have seen us in the news as well. We do some fun side projects, specifically the Joe Rogan deepfakes, and we work with a lot about astronomy and things like that. But that's a little bit about Dessa. The agenda for today: why do we care about machine learning monitoring and how it's different from traditional software monitoring? What are the things that we should monitor? What are some of the specifications we need to focus on to build a monitoring system? And I will also show an example of our own architecture and how you can leverage that and also maybe copy that for your own model monitoring system. Finally, I'll leave you with some more resources if you want to understand the topic of model monitoring a little bit better. All right. First off, why do we care about machine learning monitoring? Right? So one of my personal goals is to make sure that machine learning is more accessible to more and more companies. It would just be really great if to see more and more products and services being improved by machine learning. But from working with several companies, we found that many of them really focus on the model building part, right? So we have a lot of companies out there who are doing a lot of research, they're building a lot of models, but very few actually successfully put it into production, right? Or successfully do anything with the moving it out of the proof of concept stage. And there's actually quite a very few good reasons as to why this happens. First is, productionizing something that is so dynamic and probabilistic in nature is actually very difficult, right? As soon as you put a model in production, it starts to degrade because the data is non-stationary and your environment is non-stationary, right? And we're also finding that an increasing number of teams are getting burnt after putting machine learning in production because they just don't have the right kind of ecosystem, the tools needed. So for example, we worked with a Fortune 500 bank who built a really solid fraud detection model. It was highly accurate. They celebrated their achievements, right? But over a span of about 8 months, the model degraded so much in production, but the team was so busy monitoring many other of their aspects that they didn't really have the tools to automatically monitor them, leading to a lot of revenue loss for the company. Right? Second thing is, most model management tools right now are quite ad hoc, right? People in small organizations who are shipping one or two models, you have some ad hoc processes. Maybe there's a point person who is always constantly monitoring the data, running different kinds of tests on it. But to be able to do this in a scalable manner is not possible at the moment. And next thing we often see this is that since we're such an early stage of machine learning, especially putting it in for enterprises, very few companies are actually thinking about SLAs or even maintaining SLAs in an automatic fashion, right? So because very few companies are doing this, we're finding that people are losing trust in the models that they're putting in production because they just don't have the right tools to do that. So it really comes down to us, which I'm sure a lot of you here are data infrastructure engineers, to be able to build different kinds of platforms and different kinds of tools that our data scientists can leverage and use to monitor other things, right? Cool. So what usually goes wrong? Imagine the scenario, right? Your company has embraced ML significantly and you have several models put into production. From your busy day, you take some time to look at some of the metrics of your model and find that there is a steep decline, right? And now you need to investigate what happened. But you notice this, and then you have to ask yourself various questions, right? Is this a bug in the upstream data that the model is consuming? You don't know that, right? Is this, and if you want to dig into that further, do you know if any part of your pipeline is particularly broken? Or is it something that went wrong during the feature engineering stage? Or is there a bug in the training source code? And why does it matter? Did someone deploy a new model, right? And if someone did deploy a new model, where is the rest of the models, right? If I wanted to roll back, what is a rollback strategy to be able to do that, right? Along with that, there's other questions. For example, are we underfitting? Are we overfitting? Is the model not generalized enough, right, to work with a particular data set, right? And there's other aspects to it too. As machine learning becomes more and more accepted, there could be adversarial users and many other things that couldn't go wrong. So really, you need a solid way to be able to investigate and explore and figure out further where things have gone wrong, right? Cool. And this is XKCD put it really well, which is, currently most of the things that we do in machine learning is quite non-systematic, right? We need more systematic ways to be able to explore these aspects further. Cool. So the solution to that is really quite simple, actually, which is something that software engineers have been doing for decades, right? Which is writing tests. But more specifically, we need to be able to write tests and alerts on upstream data sets for quality in every aspect of the data pipeline. We need to be able to keep track and manage models in a centralized store with versioning in them and have an efficient rollback strategy. And we need to be able to evaluate models continuously using real-world outcomes and maintain predefined SLAs by setting various thresholds and continuously updating your models through automated retraining and recalibration, right? Since this focus on this talk is purely on monitoring, so I'm going to dig into that a little bit further. But if you want to talk about model management and other aspects, I'll be happy to discuss that during the office hour. Now, we already do a lot of monitoring for traditional software engineering. So traditional software, we can track our source code changes through CI tools like Circle CI, right? And then we do infrastructure and network monitoring. There's lots of folks here from Datadog, so things like that. But when it comes to machine learning, not only do we have to monitor that, and we also have to monitor infrastructure for machine learning, because if you have a model that is doing online inference, you need to make sure that it's maintaining the uptime. But along with that, you also have to do a lot of other kinds of monitoring. For example, you have to monitor data set shifts. You have to monitor whether things in the data pipeline have gone wrong. You have to make sure that there's a way for you to explain different kinds of models and be able to track all of these things, right? So that's why machine learning monitoring is slightly different from model monitoring. And on top of that, this has not helped with the process that before in software engineering, you would write your code, you would deploy your app, and then there would be a DevOps team who would be able to take care of your app and make sure that it's healthy. But with machine learning, you're not able to do that anymore because right now, you are the domain expert in data science, and you are the domain expert of that model. So if you transfer it over to a completely different team, they may not have the knowledge necessary to be able to tell you how to update these models or recalibrate them, right? Cool. So to be able to monitor this, we can have various different strategies, right? There's few things. So let's talk about each one of the things that we would like to monitor, and we can talk about that. So first thing is bugs in the data pipeline, right? And this can happen when upstream changes impact your downstream data consumption. Example, there could be changes in the schema itself, or there could be a sudden disappearance of a feature. And this happens quite a lot, actually. You'd be surprised. Many times what can happen is you build a model and you run it, and let's say it's doing online inference. You're seeing that all of a sudden, a particular input feature is a whole bunch of NaNs, or a whole bunch of minus 999s, right? And this could happen because something changed down the line that your model wasn't expecting, right? If it is an important feature, then that may impact your models quite significantly, right? But there's different strategies for us to be able to monitor that. What if we can write expectations that will check a data set as it goes through every aspect of my pipeline, right? Usually you will be using a reference data set to be able to train your model. So what you can do then is to create a sort of expectation all around your pipeline that will compare the newer data that is coming in to the standard that you have set with the reference, right? And this expectation should store various kinds of information about your data set. Some of the more important ones are, for example, schema checks, right? Min-max ratios, special value checks, uniqueness, etc. Right? Schema checks and all of these things are quite important, but these are things that have already been talked about for a very long time, and we already know why they're important, right? If the type of if one of your column changes, you need to be able to know that. If one of the columns disappear, you need to be able to know that. So doing schema checks on a continuous basis is quite important. But what I want to elaborate on really is the special knowledge check that I mean here. Now, we have tools that, existing tools that do all of these things, but even then you need to be able to do this in a continuous basis. But for this special knowledge check, we've seen this happen quite a bit. Now, traditionally, maybe you would build a model that is using 50 features, let's say, right? But as we are going forward with machine learning, chances are you will have models that use 100, 200, 300, 400 different kinds of features. And what we have found is that usually in a company, there's someone who has some special knowledge about a particular data set or has special knowledge about a particular data source. And in software engineering, these kind of special knowledge was communicated to the rest of the company by writing tests, right? Tests act as documentation in the source code. Similarly, tests in data pipelines and data sets act as documentation. So what you can do is, if you have a way to codify the different kind of special knowledge, maybe you know that, hey, this feature here can only be, it's a categorical feature and it can only be A, B, and C, right? To be able to write the test for that, right, and codify that is going to be quite important for you to share that knowledge with the rest of the company, right? Okay. So that's a little bit about bugs in the data pipeline, and that's one of the things that we need to be continuously monitoring as we are talking about the monitoring system. The second thing that we need to monitor is dataset shifts. And this is usually a bit more difficult to monitor and a bit more computationally intensive. Now, after deploying a machine learning model in production, it will continue to provide the estimates on the population it was trained on. But as the population shifts over time, the estimates become less and less relevant on the current population that you have, right? So simplistically, there's usually two types of data set shifts that we need to monitor, which is input drifts and concept drifts, right? So let's talk about that a little further. Input drift is referring to the change in the distribution of the input variables present in the training and inference data. Right. This occurs because data sets come from non-stationary environments, which is true for any kind of data set. It may or may not actually correspond to a drop in the model performance, but it can indicate problems in your data distribution, or at the same time, it can also indicate problems and bugs in your pipeline. Right. For example, you have a data set today that uses customer demographics as a feature, right? Let's say it's a churn prediction model, and if your competitor produces a new marketing campaign that is specifically targeting the millennial customer base that you have, that's going to show up as a distribution shift in the demographic feature that you have within your model, right? Or let's say you have a bug in your pipeline that is adding systematic noise, skewing a bunch of rows intermittently, right? This will also show up as a distribution shift within your feature itself, right? Now, not only can monitoring input drift in each of your features help you make sure that your model is performing the way it is, that your data sets are healthy, that your pipeline is healthy, but it can also help you be more proactive in choosing better features to train on. Now, why do I say that? So think about it this way. Let's say you have a feature that gives you a great result when you train your model with it. But you find out with time that this feature itself actually is quite volatile. And when you put it in as a validation set, it changes quite rapidly. Even though it may give you better results and better accuracy, you may do a trade-off in volatility, right? So you may choose not to include that as part of your training data set, right? So being able to continuously monitor your input drifts in each one of your features allows you to make sure that you are doing the right kind of trade-offs between volatility and accuracy, or your metric of choice, right? There's various ways for us to be able to monitor input drifts. And this is a well-studied, well-documented approach of comparing distributions, right? There's lots of papers written about it, but the approach that we take at Dessa is we want to make sure that whatever the things that you write or the things that you monitor is easily interpretable to the rest of the company, right? So that you, product managers and others, can set the right amounts of expectations, right? So there's three different ways. So you can have a population stability index, L infinity checks, similarity scores, or you can write a custom algorithm yourself. I personally prefer L infinity checks because it allows you to, it's very easily interpretable, right? And it's also less computationally intensive. So it takes lesser time to be able to get that value out, right? But we can talk about that later and why you would choose one algorithm over the other at a later time. Cool. So these are some of the ways for you to be able to monitor input drift, right? The next thing that comes up is concept drift. And concept drift happens when the actual function, the probability distribution of the function that you have that is mapping your target, your target to the input variable actually changes. And this always shows up as a drop in the model performance. It usually indicates your model needs to be trained again. And there's many reasons this can happen, actually. Let's take an example of an e-commerce company, right? Doing machine learning for predictive sale analysis. In this example, one reason for concept drift may be seasonality, right? Which means that shopping behavior changes with time, right? So for example, there may be higher sales during Christmas, right? And there may be lower sales during summer. And the demographic might change, right? During that time. So this can show up as concept drift that happens. The important thing about concept drift is that it can take many different forms, right? It could be a gradual change over time, or it could be a recurring or cyclical change, right? So for example, the seasonality aspect that I talked about, or it could be a sudden and abrupt change, right? Maybe you're an e-commerce company and tomorrow is Black Friday, right? If it's Black Friday, you will see a strong change in the demographics of your data set. So what different companies do is, once they monitor these things and once they know what to expect with their data sets, they may build different models for different aspects of the time, and they will swap the models that are in production. So if it's a seasonality thing, they will probably use a different model that is optimized with a different kind of demographic, right? The main key aspect of monitoring concept drift is making sure that it is tied to a production metric or a business metric that you can always track, right? And this needs to be defined by your data scientist at all time. Okay, cool. We talked a lot about some of the different aspects of monitoring that we would like to do, right? So bugs in the data pipeline, input drifts, concept drifts. And these are some of the three fundamental things that would be really good for you to monitor. There's other aspects as well of monitoring, like uncertainty monitoring, doing explainability ways to make sure that some aspects of your models are correct, right? But these three fundamental ones can really help you push your models to production faster, right? But to be able to do this, what we need to do is essentially, your data scientist needs to be able to codify expectations of data sets, right? They need to be able to say that I expect this data set to be of this particular standard, which has this much deviation, etc., right? Essentially, what they need to do is, if this is a traditional machine learning workflow, right? You have your data extraction layer, which is all of your ETLs, which is being stored in your data store, and then you're doing some data processing, feature engineering. Once you have a reference data set, you're essentially doing the training on it, and you go in this cycle here, eventually creating a trained model, which you may store somewhere, right? Once you have your trained model, you can then put it into production, either as a cron-based batch online processing, or you can do online predictions through microservices, right? But this is the traditional, very overly simplified way for you to do a machine learning system. But the main point is, you want to be able to set expectations of data sets from every single input and output that is coming into your pipeline, right? Because setting those expectations and running these tests continuously, once things go wrong, you can then tell where in your pipeline things fell apart, right? So it's very important for us to be able to put expectations and run tests on every single input and output of the black box. These black boxes can look different for your company, right? But the whole point is you need to be able to continuously monitor them through tests, right? Okay, so the way we solve this at Dessa is through our software. It's called Orbit, right? And Orbit is a combination of a Python SDK, a scheduler, and a GUI, right? That allows us to do this kind of monitoring, right? The Python SDK is used by our data scientists to be able to write expectations, right? Which I'll talk about shortly. Cool. In Orbit, the concept that we have is we have a concept of a data contracts object, right? Its data contracts is just a Python class, right, which stores a whole bunch of metadata. Right? And that's really our way of defining expectations using the Orbit SDK to be able to codify different kinds of expectations. Every data contract is essentially a configurable metadata store that cannot be mutated once it is live. The reason for the immutability is the fact that we want to be able to create a lineage of all the changes that are happening to the data sets as we go, right? So again, I'm going to repeat. Every data contract object is configurable metastore that cannot be mutated, right? All data contracts are also versioned, and all of these versions of the contract needs to be updated to be able to mutate it. Now, essentially, the way it works is you take your reference data set, which is like a gold standard data set that you think every single data set coming in needs to conform to. You create a data contract out of it, which is your expectation, and in that expectation, you will be defining different things. This is the standard deviation. This is the special knowledge check. This is the XYZ, right, which we'll talk about further. And then Orbit will continuously use the newer data sets and continuously monitor them along with the data contracts, right? So this is really our way to be able to configure and set expectations for any kind of reference data set. Now, I'll showcase how the Python SDK works right here, right? So this is kind of our approach to be able to use the data contract. So what you can see here is I'm importing the data contract library, and then I'm creating a data contract, giving it a name, and Orbit will automatically version them. And I'm passing in a reference data frame, right? Once I pass in a reference data frame, I'm going to be saving the data contract, which is essentially, it turns it into a pickle file with a whole bunch of metadata, right? And I'll save this data contract into a particular registry. And it's very important for your company to be able to maintain a registry of all the data contracts so that you can maintain a lineage, like I mentioned earlier. Once I do this, using the Python SDK itself, I can configure various aspects of the data contract. So I can say things like, hey, this contract with this data set needs to conform to this kind of L infinity check, right? Or there needs to be, at any point in time, this particular column can only have this many number of NaNs, or this many number of standard deviation, or different kinds of other checks that you would do, right? Along with that, I mentioned earlier that, there's a few things. Data science is evolving so rapidly, right? So the checks that you would do in your data sets may change rapidly. So you need to be able to write your own algorithms and add them as monitoring, right? Second aspect is that your machine learning engineers need to be able to essentially keep up with the newer methods that are coming in and be able to codify them. So what we also did is we provided a way for our machine learning engineers to create custom methods and pass them into the data contract itself, right? Once they do that, they can define any kind of algorithm that they want on the particular types of column. But there is some stuff that comes out of the box, right? Once you configure these things, you will be essentially running a validation report, and this validation will be done in a different script that you will write, right? So you write the script, and then that script will be continuously be running in the background, right, on a different cluster. It'll be pulling the data set from whatever you define, whether it's Kafka, whether it's your SQL database, wherever it is. It'll pull the data set, and it will run continuous validations, comparing it to the data contract that you stored earlier, right? Once you do this, all of these reports get surfaced into a GUI through the REST API. And in this REST API, you are able to essentially see all the schema checks, the population shift, and all the custom tests there, right? So this is really our way to be able to configure different kinds of metadata about a particular data and continuously run these tests, right? Okay. That data contract concept works really well to be able to find input drift and to be able to do bugs in your data pipeline. But it falls apart when you're doing a concept drift, because in concept drift, not only do you have to monitor those things, but you also have to monitor different kind of algorithms that are tied into your own business logic. So what we do for our data scientists is provide them ways to track different kinds of production metrics, right? Whether it's accuracy, the revenue, number of active customers, anything that the data scientists have the power to decide which algorithm or what to use to tie into the business metric. All of these things eventually get fed back into the validation report, right? Which gets monitored on a continuous basis, right? And these the way we do continuous is I'm going to define that shortly. But this is essentially, you can use not only you can use something like this, but you can also use something like Datadog if you're already part of the Datadog ecosystem, right? Cool. So what happens at the end, by giving our data scientists the ability to do these things, we now have the ability to write expectations. So every green field is an expectation. We have the ability to write expectations in every aspect of our data pipeline, right? For example, in the training data set, I can now write a data contract that is taking this training reference data set as a metadata and then publish it to Orbit, and Orbit will continuously monitor this process to make sure anything that new that is coming in is conforming to that data set, right? Cool. Before I jump into the architecture of Orbit itself, I mentioned that we need to be able to monitor bugs in the pipeline, which is through data contracts and concept drift. But there's also other criteria that we need to think about before we build the monitoring system within the company, right? Some of them are, the first thing is it needs to be a sidecar or async architecture. The reason for this is that doing these validation checks on such big data pipelines is very computationally intensive, right? And it takes a long time. So you don't want them to be tied into the cluster that is running your app, right? Or running the production model. All of these things should be happening in the background and should be happening asynchronously. Along with that, you need to be able to provide some standard monitoring features. For example, schema checks, min-maxes, L-infinity checks that I talked about, right? Which your data scientists don't have to define again and be able to just use automatically, right? Next up is you need to be able to define custom monitors. So that's where the custom method comes in, right? We need to be able to define custom Lambda functions so that we can run different kinds of algorithms on each one of our functions. And then this is where the scheduling comes in, right? Once you create these monitors, not only do you need to be able to do these checks on a cron-based schedule. So for example, you could say like, hey, run this monitoring every single day at this particular time, right? Not only do you have to do that, but you also have to do it on an event-based approach. Because, for example, if you have a Kafka system, you want to be able to say, like, hey, as soon as I'm consuming a particular topic, trigger this monitoring system, right? Or as soon as this data set is available, trigger the monitoring to make sure that it is conforming to it. Lastly, you need a way to be able to view all of these things in a centralized place, and at the same time be able to set thresholds on them so that people get notified, the code owners get notified of each one of them. So whoever the project owner of that is. Cool. So what this eventually leads us to is an architecture like this, right? So what we have here is the data contracts approach that I talked about earlier. But this is what the architecture that we built for Orbit, right? Essentially, your data scientists use the Python SDK to be able to write different kinds of monitors, right? And each monitor is essentially a Python script you can think about, right? And in that Python script, they will be defining where to pull the data contract from, where to pull the data sources from. So where's the input going to be? What is the reference data set? And to be able to run the different kinds of validators that we talked about earlier, right? When each one of these monitors, you create each one of these monitors for every single aspect of your pipeline that you want to monitor. And then you publish it to Orbit, right? And you publish it through our REST API. And once you do that, you can then set triggers to run these monitors, right? So you can say like, hey, run this monitor at this particular time, or run this monitor when the new data set is available, or when a different kind of event happens, right? All of those things then eventually get fed into a data store. And in that data store, our REST API pulls up all the validation reports, and you can then view them in a centralized place across all of your data science projects that you have ongoing. So now, with this ability, you have this way for you to be able to monitor every single aspect of your pipeline across all of your data science projects, right? Eventually, from the GUI itself, you can set various kinds of thresholds. So you can say things like, hey, as soon as the PSI ships by 0.1, notify X on PagerDuty, or notify them on Slack, or send them an email, right, to make sure that they know what's going on, right? That's really the heart of it. One of the more important aspects of it is to make sure that you have the ability to store all these data contracts in a centralized place. Because this ability will eventually tell you a history of every single data lineage that is happening across all of your pipelines, right? So doing this versioning and doing this immutable approach is very, very important for you to monitor. So concretely speaking, this is the data scientist workflow that we would be having. You create a data contract here, like you can see. Right? I'm defining different kinds of min-maxes tests. I'm setting different kinds of lower bounds. Or I could do my own custom method if I wanted, right? And so you can set different kinds of threshold there. And then I'm saving the data contract. Currently, I'm saving this locally, but you would traditionally be saving it into your own contract registry, right? And then you would place these data contracts in your validation code. So you can see here that I have a validate.py, right? And this is the monitoring code that I will be running on a cron-based approach. So I'm loading the data contract, and I'm running the validate on the X inference that I received, that I got earlier from my data store. Once I do that, I will deploy the validation pipeline, right, on using Foundation's monitor, which is Orbit, and that will be deployed on the cluster, on the monitoring cluster that I have built in, right? Once that is done, all of my monitor scripts will be in this single project. So you can see I have a fraud project here, right, and I have 2 monitoring scripts here, right? And then I can go into each one of them, schedule different kinds of timing, right? Or I can set an event-based one, and Orbit will automatically generate validation reports on a continuous basis. After that, I can go into and see each one of the validation results, and I can see things like, hey, the out-of-the-box ones, like schema checks, population shifts, special values, min-maxes, etc. I can continuously see which one is doing what, right? I can see that, hey, this population shift here, there's something critical that has gone wrong. Maybe one of the features have shifted quite a lot, so I can go into that and dig into that further. And then I can set different kinds of thresholds to be able to monitor them on a continuous basis, right? That's we covered a lot today. I want to quickly summarize what we talked about. The first thing we talked about is why monitoring is important, right? And how monitoring machine learning models is different from monitoring traditional software, right? We also talked about some of the 3 fundamental ones that we should monitor, right? Bugs in the data pipeline, in every aspect of your pipeline, being able to monitor dataset shifts through input drifts and concept drift. And then we talked about how our framework of doing it, which is using data expectations, data contracts, which act as expectations for every single aspect of your pipeline. And then lastly, we talked about the architecture that we built, which is a sidecar architecture that runs on a separate cluster, which can run all this monitoring on an event-based or a cron-based schedule to be able to validate your reports on a continuous basis, right? That's all I have today. Thank you very much. Appreciate it, and I'll take some questions if there's any.
Awesome talk.
Thank you.
I love that we have independently converged on using expectations
That's
as a
right,
language.
yeah.
That's just amazing. Yeah. You talked about special knowledge checks. I'm curious what that means in the framework.
Right. So what we found is that there are individuals within the company who know something special about a data set, right? What I mean by that is they have this particular knowledge about it, which others don't, right? For example, someone may be really deep down into a particular data set or a particular workflow, right? Working on a project, and they may have this like intuition about something, right? Or they may have some more concrete, formal ideas like, this is a categorical feature, and it can only have A, B, and C categories, right? But you need to be able to codify those things, right? And write them as expectations, right? So that A, it acts as documentation for the rest of your company, right? And B, all of these special knowledge ones are maintained and continuously checked.
Got it.
Does that kind of make sense?
It does.
Yeah.
And what I wasn't sure is, are you like pausing the pipeline to ask somebody a question, like look at this? It sounds like no, instead you're saying, hey, prior to running the pipeline, let's generate a Lambda together.
That's right, that's right, that's exactly it. So no, we're not telling anyone to stop their pipelines, right? It's whoever is working on the project itself, it's up to them to be able to make sure that they're creating the Lambda functions that are able to monitor those things, right? Yeah.
Cool, yeah, thank you.
Thank you, yeah.